we are going to deal with the converse direction. So suppose that A is an interval. Suppose that A is an interval, and suppose that A is an interval and not connected. Suppose that A is an interval which is not connected. So what does this imply? If A is not connected, then this implies that then there exists open sets W1, W2 in A. The open sets, there exists open sets W1, W2 in A with W1, W2 being non-empty, distinct. Next is open sets W1 and W2 in A, which are non-empty, distinct, and they are disjoint. And W1 intersection W2 is an empty set. Is an empty set. Is an empty set. Then now we can write A, because W1 and W2 now form a separation of A. So A is W1 union W2. They form a separation of A. So that's what we are having. Now we want to show that A is not an interval. So what do we observe? You observe that W1 and W2 are non-empty. They are non-empty. So W1, I'm assuming that W1 is there, W2 is also here. W1 is non-empty. So we have some elements in W1 and W2 is non-empty. And we also have some elements in W2. So since W1 and the W2 are non-empty, so we are going to let A be an element in W1 and B be an element in W2. Then we are going to define, remember W1 and W2 they are disjoint, so A and B they are also distinct. So A is different from B since W1 and W2 do not meet. So we are going to define, two sets, W1 star and W2 star. So W1 star, I'm going to extract it from W1 star. W1 star consists of real numbers. It consists of real numbers. Remember, A is here, A is there, also B is here. So WA consists of real numbers. Real numbers. It is this set. W1 star is this set. Somewhere around here in W1. W1 star is somewhere around in W1. So W1 star is this set. A X. We are having this set consisting of real numbers. In here, such that so it's like I'm taking this interval such that this set cannot meet W2 because I'm extracting it from W1. So real numbers such that real numbers in here, such that they do not meet with W2. Also, W2 star consists of real numbers such that real numbers in there. So I'm extracting my W2 star from there. Real numbers such that they do not meet with the W1. So I'm having those two sets. So you observe that this is W1 and this is W2. So you observe that W1 star is bounded above by B. W1 star is here. So you observe that B is an upper bound of W1 star. Observe that W1 star is bounded above by B and by the completeness axiom. W1 star has a least upper bound. W1 star has a least upper bound. And by the completeness axiom, W1 star has a least upper bound. So let C be the least upper bound of W1 star. What do we observe about that least upper bound? Observe that W1 star is bounded above by B, and by the completeness axiom, W1 star has a least upper bound. So let C be the least upper bound of W1 star. So then, if C is the least upper bound of W1 star, then we have C is the least upper bound. So this C should be less or equal to, remember B is the upper bound, so this C should be less or equal to B, should be less or equal to B. This B is the upper bound, and this C should be less or equal to A, since A is an element in W1 star. All elements in W1 star should be less or equal to C. So that's what we are having. Now, since A is an interval, remember point A and B, A was in W1 and B was in W2, which W1s and W2 are subsets of A. So that means A and B are in set A, and A is different from B. Now, if C is a point, which is in this form, then if C is a point which is in this form, and we know that, and A is an interval, then this should imply that since A is an interval and we are having a point which satisfies this relation, this should imply that C is a point in A. C is a point in A. But W1 and W2 form a separation. They form a separation of they form a separation of set A. W1 and W2 form a separation of A. And C is a point in A. And C is a point in A. and we are separating A into open sets W1 and 2. So that implies that C is either in W1 or C is in W2. Since W1 and W2 form a separation of, they form a separation of A. So then C is in W1, or C is in W2, or C is in W2. So without loss of generality, suppose that C is in W1. Suppose that C is in W1 and W1 is an open set. And W1 is an open set. Suppose that C is in W1 and W1 is an open set. This implies that for some epsilon greater than 0, the epsilon neighborhood of C for some epsilon greater than 0, the epsilon neighborhood, by definition of an open set, the epsilon neighborhood of C is fully contained in W1. For some epsilon greater than 0, we have epsilon neighborhood of C fully contained in W1. Then remember, W1 and W2 do not meet. Then C minus epsilon, C plus epsilon, intersection with W2 is an empty set. Why is it an empty set? Because W1 and W2 are disjoint. So since they are disjoint, also this set intersected with W2. Since this set is in W1, it cannot meet with W2, since W1 and W2 are disjoint. So then we shall have this. So what does this imply? So I have my point A somewhere. I also have my point B somewhere, and also my C in there. So I'm considering the epsilon neighborhood of this C. So I have C plus epsilon, then C minus epsilon. This is the W1, this is W2. So if I consider, if this is C plus epsilon, so this will be C plus epsilon over 2, this point here, this point there. So what does that imply? So that implies that I'm going to consider this set now. I'm going to consider that set from A to C plus epsilon over 2. Remember, this is W2. This is W2. This is W1. So what does that imply? I'm going to consider this set. So since we have this, also this set A, C plus epsilon over 2 cannot meet with W2. So you observe that this set here, somehow resembles something. You remember how we define W1 star? It is consisting of real numbers which satisfy this relation. So now we have this relation here. It's like where there is X, we have substituted with C plus epsilon over 2. So that means that, and since we have this, then C plus epsilon over 2 is an element in W1 star. Is an element in W1 star. But what can we observe this? But we said that C is the least upper bound. C is the least upper bound of W1 star. C is the least upper bound of W1 star, and we are having C plus epsilon over 2 greater than C. C is the least upper bound, but we are having an element in the set which is greater than the least upper bound. This is a contradiction. We are having an element in the set which is greater than the least upper bound. This is a contradiction. Implying that this is a contradiction. It's contradiction to the fact that C is the least upper bound. Contradiction to the fact that C is the least upper bound. So this implies that our assumption was actually wrong. This implies that now C is not an element in W1. C is not an element in W1. I can repeat. From this relation here, we have concluded that C plus epsilon over 2 is in W1 star. But C is the least upper bound of W1 star. Then that implies that we are having an element in W1 star, which is C plus epsilon over 2, greater than the least upper bound. That is a contradiction to the definition of the least upper bound, because every element in the set must be less or equal to the least upper bound. So this implies that our assumption that C is in W1 was wrong. So since it is a contradiction, then we have C not being in W1. So implying that C, it's contradiction to the fact that C is in W1, and also this C shouldn't be the least upper bound of W1 star. I can also put that C is now not the least upper bound of W1 star. C is not the least upper bound of W1 star, and hence, remember we said that W1 and W2 form a separation of A. Now since they form a separation of A, we had this. Now since C is not in W1, hence also W1 and W2 do not form a separation. Do not form a separation of A. Do not form a separation of A. Hence A is connected.